So this assignment related to work energy and power. First, we'll discuss the doubts related to the assignment. The first question is question 6, part C. In this question, when a flea jumps, some of its energy comes from the leg muscles and some from the compressible pad behind the back leg. The pads are made from a protein which is called wrestling. Before jumping, the pads are compressed. On takeoff, the pad expand and energy transferred. You can assume that each pad is a cube of 60 micrometer side, which is fully compressed until the depth of the pad is negligible. For a particular jump, the total energy transfer from the pad and the lag muscle is about 0.8 microjoules. Calculate the percentage of energy for jump that comes from the two pads. The Young modulus is given and the strain is also given. So how we can work out how much energy being transferred? So what we will do, we will basically work out the elastic strain energy, because as it is compressed, when something deform, it will have elastic strain energy. So we'll work out the elastic strain energy. Elastic strain energy is given by formula half force into extension or force into compression. We already have the extension or a compression because, as you see in the question, that we assume that it does not change the area. Only thing what happened, it compressed to 60 micrometer. So 60 into 10 power minus 6 meter, the compression is there. So first we need the force. And after getting the force, we'll get how much elastic strain energy is there. And then we'll find the percentage compared to total energy, because this was a total energy supplied. This is the total energy supplied, but that total energy, like not all of it is converted to elastic strain energy. So we'll find what percentage is there converted. So main thing is, first we have to find the elastic strain energy in the legs. So half force into extension. We have the stress here, that's given. We have the strain is also given, that is 1. So using the stress and strain, we will find the force, because we have the Young's modulus in strain is given. So using the stress and strain ratio, which is because the ratio between stress and strain is equal to Young's modulus. So the Young's modulus, which is normally denoted by E, equals to stress divided by strain. And stress is force acting on unit area. So Young's modulus is F divided by A, and strain is change in length over original length. When we simplify this equation, so the Young's modulus will be F L divided by delta L and A. So what we need, our subject is a force, because we want the force here. So if we need force, so elastic strain energy multiplied by change in length multiplied by area divided by original length will give us the total force which it experiences. So the Young's modulus is there. So Young's modulus was given 1.8 into 10 power 6. So 1.8 into 10 power 6. The ratio between, because the strain is given 1 here, so it means like change in length over original length equals to 1. So we can also say that like this value, change in length over original length, is equals to 1. So it does not make difference. And what about area? So area, because it's a cube, so it is length into L square is there basically. That's the area. So 60 micrometer. So area will be 16 to 10 power minus 6 square. And that will give us the applied force. So when we simplify this, we'll get how much force it will experience. the force will be 6.48 into 10 to the power minus 3 Newton. That's a applied force. After getting the force or after finding the force, what we'll do, we'll find the elastic strain energy. How to work out the elastic strain energy? And that will be the elastic strain energy in one leg. But as there are two legs, so it will be multiplied by 2. So elastic strain energy is half force into extension. So elastic strain energy is half force multiplied by extension, or in this case is a compression. Half, the force is 6.48 into 10 to the power minus 3, which we calculated. And the compression is 60 micrometer, so 60 into 10 to the power minus 6. When we simplify, it will be 1.94 into 10 to the power minus 7 joules. That is the energy for like elastic strain energy stored in each leg, one leg. But because the total energy, so what we'll do, we'll multiply by 2. And now we need the percentage. What percentage? Like the total energy which was supplied was 0.8 microjoules. The total energy which we supply was 0.8 microjoule. But how much, what proportion is converted, or what percentage of energy for the jump that come from the two pads? So from the two pads, this is the total energy, 1.94 into 10 to the power minus 7 multiplied by 2. And then it is divided by the total energy supplied, 0.8 into 10 to the power minus 6, and then into 100. Because we need a percentage, that's why we are multiplying it by 100. So when we simplify, about 48.6% of the energy for the jump is coming from the legs or the pad. Is it clear discussion? Question 6, part C1. In the second part, suggest two properties that make it suitable to assist the jump. So why the jump will be assisted by using a pad, like a protein is there. So why it can assist or help the jump. First thing, it will have a like example for a material to transfer greater amount of energy, like with a small force. So it should have a low stiffness or low Young's modulus, because if it is having a high Young modulus, then greater amount of forces or energy is a greater amount of force basically is needed to produce a small deformation. But we want it to deform, because if it deform easily, it means it can store greater amount of energy. So it should have a low Young's modulus, like it should deform easily, and it should not deform plastically, because if there's a plastic deformation, most of the energy will remain in the object and very small amount of energy will be transferred. That's why we want the maximum amount of energy to be transferred, and it should be compressed easily. So it should have a low Young's modulus, as we don't want it to transfer or to store a lot of energy, or we don't want the greater amount of force, because we want a small amount of force should deform it so it can easily compress. And so it should have a low Young's modulus, and it should have a high elastic limit. Why high elastic limit? If it was not having a high elastic limit, maybe when it is deforming, it might deform plastically or permanent deformation may occur. So it should have a high elastic limit and low Young's modulus, so that greater amount of energy can be stored, and when it is released, most of the energy should be released. So low Young's modulus, what is the advantage? That a small force can deform the pads. And high elastic limit means when it deformed, because when it returned back to its original shape, it can transfer most of its energy. If it was having a low elastic limit, a small elastic limit, then it might deform plastically. As a result, it cannot assist the jump, it cannot transfer greater amount of energy to the body. Next is question 50D1. This is 14 number 7. 15A B1. In this question, inside the pogo stick, as you can see, the spring is compressed. Uh, what happened? It is converting the elastic strain energy to the potential energy. Potential and kinetic, basically both energies are there. The doubt was 15B1. So inside the pogo stick, the spring is compressed by 3 centimeters. A child jumps onto the foot of the footrest of the pogo stick, and the spring compresses 6 centimeters, further 6 centimeters. The pogo stick and the child move at a maximum height at position 3, you can see. Then the spring compressed by 6 centimeters, this is original length, and the pogo stick and the child has a maximum height. Use the graph to show that the work done by the child on the spring is about 130 joules. Look, if we have a force and extension graph or force and compression graph, area under the graph will give us the energy stored. The total area under the graph simply give us how much energy will be stored. So what we have to do, we have to, if you read the question, they mention already inside a pogo stick, the spring is compressed by 3 centimeter. So spring is already at 3 centimeter, like compressed to 3 centimeter. But as the child jumps onto the footrest, the spring compressed further by 6 centimeter. So we have to find how much energy supplied or how much work is done by the child. Like when the spring was compressed 3 centimeter originally, because the pogo stick is also having its weight, so spring was already compressed in the pogo stick. That is the total energy which was already there in the spring. Now what the child did, he compressed further 6 centimeters. So if he compressed further 6 centimeter means what position the child has compressed this to 9 centimeter. So child compressed this to 9 centimeter. We want how much work is done. Like this is already amount of energy was stored in the spring, and how we can work out it is half force into extension or force into compression. Then this is the extra amount. So basically what we have to do, this is a new position of a spring. So spring was originally compressed. Say this is a normal length of a spring in a pogo stick. The spring was compressed by 3 centimeters when it was there in the stick. So this length, this is 3 centimeters. But as the boy pushed this, the spring further compressed by 6 centimeters. So how much the total compression is there? The total change, that is a 9 centimeter, because he further compresses 6 centimeters. So total new position will be 9. We want to find how much energy is or how much work is done by the child. So what we'll do, we'll find area of this part to know how much energy was there in the spring initially. Then we'll find area of this part. Like again, you can use half base into height and find the energy of this region. And then you subtract the two to get the how much work is done by the child. Or there's also another way you can use a trapezium. Like this was already there. This amount of energy is already there in the stored in the spring. So this was the energy stored in the spring initially. This is a new position. So new position, this will be the new position. So what we will do, we want how much work is done by the child. So we need only this region from 3 centimeter to 9 centimeter. So we just find the area of this part. We don't use this part. We just find area of this part to know how much energy or work done by the child as he compresses the spring. Is it clear, this one? And you can use trapezium here. It is a half sum of the parallel side into height, or you can divide this into triangle and a rectangle. You can divide this into triangle and rectangle, or you can use a trapezium to work out how much energy is supplied or work is done by the child. So this was originally, it was 3 centimeter compressed. This is done by the child. But because if the total change to 9 centimeter, 3 or centimeter was already, like originally it was compressed 3 centimeter and a boy further compressed to 6 centimeter more. So it means the total compression become 9 centimeter. So we want to find how much energy is supplied from 3 centimeter, or how much work is done to change its length or to compress from 6 centimeter to, from 3 centimeter to 9 centimeter. The total change will be 6 centimeter. And don't forget to convert the unit. Here it is written in kilonewton and compression is in centimeters. So it will be, should use in meters, because SI unit of length is meter and force is Newton. So final answer should be in joule. Is it clear now, this part? Then next question is 17B2. The photograph shows an exercise device and someone using it. The device contains two rubber cords which are extended when the device is used. A student investigates the property of a device by hanging a weight on it and measure the extension. The student obtained the following graphs for her results. The doubt was 17B2. The student set up the spreadsheet to investigate the work done in stretching the device each time a weight is added. Why the spreadsheet result is overestimation? Look, why it's an overestimation of a work done. You can clearly see that the change in the load, like what student is doing, that changing a load by 10 Newton every time, like 0 to 10, then 10 to 20, also 10 Newtons, 10 Newtons, 10 Newtons. So what might happen? Maybe the spring might deform after it reach 50, or after it might reach 60, it might deform. So as a result of a deformation, its change in length won't be same. So student is changing the length, changing the force with a greater magnitude. Like example, every time changing it by 10 Newton, it's a big change in terms of force. So due to this force, like maybe as the spring might compress, so here the extension, or say at 40 or at 50, it was 14.5. But at 60, it shows it is 20, but maybe at 58 also, or at 55 also, it is 20, because we are changing a load too much, we are changing the force too much, so we are not getting numbers in between. So the work done, which is a product of force into distance, and in this case it will be half force into extension or force into compression. So why this work done is a overestimation, because the change in the force every time student is changing the force by 10, a greater number. So that's why this is overestimation. If student was changing like every time by 1 Newton or 3 Newton, then it will be a more closer to the practical value. But every time changing the force with a greater difference between the two values shows that this is overestimation. Like maybe the extension may not be same as what we calculated. If it was say 55, maybe the extension was 19.0. When it is 65, when it is 55, extension might be 19.0. 65, maybe it is 25. Because as a spring might deform, as a result, what will happen? It will be an overestimation. Is it clear, this part? 17D, explain whether more or less work would be done applying the same maximum total stretching force to a similar exercise with a rubber cord twice the cross-sectional area. So if we change the cross-sectional area, what will happen to the work done? So whether more or less will be done when the same maximum stretching force, we are applying the same force to a similar exercise machine with a rubber cord that is twice cross-sectional area. Look, the change in the volume is same. So volume is equals to area multiplied by length. Now what happened? If we double the area, the change in length will be half. Like say volume is area multiplied by length. First the area was 2 and say length, the change in length was 5. So area multiplied by length, we were getting 10. But now we did what we did. We double the area and applying the same force. So change in volume will be same. So if the volume change is same, so area is double, area become 4 now. Because first it was 2, now 2a means the area become 4. So what will happen to exchange length, the change in length, that will be 2.5 or half of the original one. So because the force is same, so change in volume will also be same for both cases. But the only difference is that if you are using a large area, then the change in length will be smaller. If you are using a small area, then change in length will be greater. But the total volume change, as the force applied is same for both conditions, that's why the volume change is same. Now, if the change in length is smaller, what happened to the work done? As they are asking whether more or less work could be done. So work done is what? Work done is half force into extension. Force is not changing, as I mentioned, force is same. But as a result, if area is double, the length will become half. If length decreases, what happened to work done? The work done will also decrease. So less work will be done compared to the original one. So originally, if it was having a small area, we can stretch to a longer length, means we are doing more work done because the force is same. But later what happened, if it area is double, so the length change in length will be half. As a change in length is half, it means less work will be done to deform. So if work done is less, the elastic strain energy is half force into extension. So less work will be there. So next out is question 27. Which of the following is not a unit of energy? So when we work out, the first one is written Newton second inverse. The second one is written kilowatt hour. The third one is Newton meter, and the fourth one is watt second. So energy having different formula. Energy is power multiplied by time, because power is energy divided by time. So unit of the power is watt or kilowatt, and if time is in hours, so kilowatt hour. So kilowatt hour is a unit of energy. Then work done is force multiplied by distance. Work done is joules. So force is Newton and distance is meter. So Newton meter is also unit of energy. And same thing, if power is given in watts and time is seconds, so watt second is also unit of energy. So which is not the unit of energy? That will be option A.